Wonderful. Well, thank you very much for the introduction, and thank you everybody for taking some time coming to hang out together. Getting the skills to make a good fan selection is core, and we're gonna start foundational today and work our way up. So, with that said, let's get rolling. When I said foundational, I definitely meant foundational. I just got to get on the right screen. Let's start out with the fan laws, right? So fan laws are really important. What it allows me to do is take a data set, whether it's a test and balance report or it's data from a manufacturer, and it's allowing me to take a starting point and translate that to what I need in the future, whether it's more air, um, different RPMs. So fan laws are really foundational and they help build fan curves. So let's start here. The first fan law, I call this the fun fan law. Everybody loves this one. All it tells me here is that as I change RPM, my CFM is going to change 1 to 1, right? So if I need 10% more air, I simply need 10% more RPM. Makes everybody happy. Second fan law, though, this is the one that it's the uncomfortable fan law, right? It says as I change my RPM, as I start moving more air, the static pressure I need to overcome changes to the square, right? So that 10% increase in CFM we just got, it did result in 21% more static pressure to overcome. Then we work into the third fan law, right? And the third fan law is what I refer to as the expensive fan law. As we change RPM and CFM, the horsepower needed to move that air will change to the cube, right? So 10% more air going to require 33% more horsepower. And kind of keep these in mind here because what we're doing is we're starting off with a good selection, right? That's where we're building up to in this webinar. Um, and if everything was a perfect selection up front, you might not need these rules as much, but a lot of times we're just reacting to what is in our industry as well, whether it's a building that you're refurbing, um, or a few extra bits of static pressure that you didn't expect. These are just kind of foundational rules. Now we're going to walk into fan curves, and first thing I want to say is I did not personally invent fan curves. um, the Air Movement and Control Association, AMCA, um, lays out guidelines, right? This is how you're going to take your data as a manufacturer. This is how you're going to record it. This is how you're going to display it. We're going to come back in as a big brother and make sure you're doing the right thing, right? So none of this is created by me or my employer. We just follow these rules and strict rules. So anybody that has that AMCA sticker, we're apples to apples. We follow the same rule set. All right, so let's move right into fan curves. First thing about a fan curve, right? This is what we're looking at right now. Across the bottom x-axis, this is volumetric flow, right? This is how much CFM I'm moving, right? Across the primary y-axis, we have system resistance. This is your static pressure, that amount of pressure I have to overcome to move the air that you're needing. And then we have a secondary axis over here on the other side, and that's brake horsepower. Now, a little lingo 101 here. There's a big difference between brake horsepower and horsepower. From a manufacturer's point of view, if I state HP, horsepower, I'm telling you that this is motor nameplate horsepower. If it is brake horsepower, that is communicating the power consumed at that point of operation, right? So let's break into the different widgets we have on our fan curve today. And I am using our Computer Automated Product Selection, or CAPS, selection program to bring up these fan curves to show you. First things first, that red arc, right? That is our fan curve. That represents the fan I'm looking at, all the test data that I got from those test procedures and recorded, right? So this is real stuff. And that's going to show how this fan will perform at this RPM. And we can see up in the left corner there, um, I'm representing 1448 fan RPM. And I say fan RPM because if this was a direct drive, the motor RPM and the impeller RPM are the exact same. But if I'm in a belt drive, then my motor RPM could be different than the impeller RPM. And this is actually discussing the fan or the impeller RPM. All right, moving on, we have this blue dashed curve. This is a representation of the system resistance that you've given me, right? This is what I have to overcome to move the amount of air you want. Kind of notice that that's parabolic in a way. Kind of interesting. If you look at the fan laws and notice as static pressure changed the square of RPM and CFM, actually displays or explains the shape of that curve. Now, the really cool point is where the two intersect, the fan curve and the system resistance curve. This is known as your operating point. This fan at this RPM, when, well, for our scenario here, 2 inches of static pressure will move 1200 CFM, right? So if that is my operating point I'm looking for, this is the right fan for me. Now there's some more information that is available across here. This black dashed line, this is your brake horsepower curve. This is representing how much horsepower it took to move that air to hit that operating point at the different points, right? And the way you read this curve, the curve could be below our operating point, above it. It's really wherever you put it to make it easiest to read. And the way we read it is we take our operating point and draw a line until we hit the brake horsepower curve. And then we're going to just draw a line over to the secondary axes. And this then shows, hey, to move 1200 at 2 inches, it's going to take 0.85 brake horsepower at that point. All right, basics of fan curves. And fan curves truly, I mean, this is a language, folks. If I'm speaking German and you're speaking Spanish, we may not understand each other and communicate perfectly, right? That's what fan curves are for our industry. This is a language. We need to speak the same language so that I'm communicating the right stuff and you're able to consume that. All right, so into the do not operate zone or don't go in there. This is this gray shaded portion. Now, this fan can pretty much operate at any point on this curve, right? This area right here, the manufacturer is telling you this is not a good place to operate. You want to stay out of this spot. And there are, several good reasons why you don't want to operate a fan in here. Kind of looking into these a little bit. Let's zoom in. Here I've got my fan curve. I'm going to draw a line, right? And in that line, we'll call that 2.2 inches of static pressure. First thing I notice is that I'm intersecting my fan curve at 2 points. Okay, so where the system resistance crosses the fan curve, that's my operating point. All of a sudden, I have two eligible spots at this RPM, at the static pressure, that I could operate at. So which one is it going to do? Is it going to move, your 300 or 2700 CFM or 700 CFM? Uh, I don't know. The fan does not know which one to do. This is going to create a scenario typically called hunting, right? It's going to go from the bottom end, say that 100 CFM, it's going to start loading up and it's going to operate at 700 CFM and then it's going to quick unload and it's going to go back and forth between these 2 points. It's going to be hunting. I kind of compare this to going 55 miles an hour down the highway with a stick shift car. You're in fifth gear and then you change to second gear and then you go back to fifth and then back to second and back to fifth. If you were to do that to your vehicle, that vehicle would not last very long. And really, I'm telling you the same thing about a fan. If a fan is left in a hunting state, it will destroy itself. All right. So that's just one of the bad things that can happen in the do not operate zone. A couple more things, like there's stall, surge, there's these different things that can happen. Stall typically occurs when your CFM is too low compared to the attack angle of the impeller, right? Thus, you start losing the ability to push the air forward. Um, this is when you have a much larger fan and a very, very low flow CFM, right? That can cause stall. So there are different things that can happen in this zone, and pretty much every manufacturer is going to kind of highlight this space and say, do not operate in this space. This is not going to be healthy. All right, basic fan curve 101 we just completed. Now, there's some other curves out there that are very valuable. Different softwares will offer you. So let's just kind of look at a couple of them. First one I'm going to look at is just an RPM curve, right? Something to know about RPM and a fan curve. When I speed up or slow down a fan, that's going to offset the fan curve that you see parallel, right? So our curve here was 1448 fan RPM. You can see 1687, 1926, literally that fan curve is offset. And as that's offset, you interact with a new point of the system resistance curve, therefore moving, well, more CFM at 1-to-1 and more static pressure at the squared. So this is kind of a neat to be able to like, okay, what RPM is going to net me what capabilities or what operating point? Before I hammer into other variable curves that are available to us in the industry, let's just step back real quick and do a quick reality check, right? I see fan curves as a living thing, right? Even though it's not a submittal, it's pretty static. I see it as living. And let me show you what I see. So right here, I have overlaid the same selection we just had, 1200 CFM at 2 inches, running at 1448 fan RPM. What were to happen if during installation, the electrical or the fire piping was run right where the designer had intended the perfect straight run for ducting? What would happen, right? So all of a sudden our ductings, it's shading a little left, a little right, got a couple extra elbows that I wasn't accounting for in design phase. Next thing you know, I got a little extra static pressure or even a lot extra. So let's represent this on this fan curve. I'm just going to add a 1/4 inch. Notice that that system resistance curve arced up, right? And this is only a 1/4 inch. Now, my new intersection point at 1448 fan RPM has me moving, let's call it 1100 CFM. Great, but that's not what I paid for. I paid for 1200. To get back to what I asked for, I need to speed this fan up. Okay, harking back to those fan laws, this all follows along. When I speed that up and get my intersection back at 1200, now this fan is moving 1525 fan RPM. And mind you, I overcame just a 1/4 inch of static pressure, right? If I were to have more and more static pressure, say I'm a 1/2 inch or an inch of static pressure off, that blue system resistance line is going to keep arcing farther and farther, even crossing into the do not operate zone, right? So this is something when we're doing fan selection as we move forward with this webinar. You know, what is a good fan selection? Well, I'll put my cursor on here. Selecting a fan just inside the good spot right here might not be a good fan selection, right? Simply because any extra static pressure and my system resistance curve is going to arc me into the do not operate zone, right? So right off of the do not operate zone, probably not the safest of selection points. All right, kind of back on task here. I was able to get back to 1200, 1525 fan RPM. And the same works in reverse as well. right? If I overshot by a quarter inch, what happens? Well, let's lay that curve down a quarter inch. Now I gotta slow my fan down to only move 1200. And this is going to represent about 1365. Okay, kind of what's a teachable point here. If I have a fan, now I'm starting to play with the technology I've selected as the engineer and saying, hey, does my fan have the ability to slow down? Is it a belt drive where I can change the relationship between the shiv and the pulley, right? Driver and driven. Is this a fan that is running on a VFD or an EC motor where I have quick access to easy balancing, right? So, and this entire thing I just showed you was just plus and minus a quarter inch. So you can see the value of having that variable nature built in, or what you might have to do to a selection after the fact to overcome plus or minus a quarter inch. All right, nice little reality check. We'll move back into some more curves, right? So right here is what we would call a min-max fan curve. I love this curve. And I can tell you this right off the bat, I will not make a selection of a variable speed fan, one with an EC motor, what I would call very green, or one with a VFD. You know, I would not make a selection without looking at this specific curve. But let's look at the pieces and parts of this.
It's
The
worth, hey,
red,
Greg,
ooh, absolutely.
it's worth noting too, if it's a variable volume application, it's good to look at this curve. But even if it's a constant volume application, it's really good to look at this curve because one of the things that I don't know if you're going to mention it eventually, but all these curves that we're looking at, they're all based on AMCA rated data, and AMCA rated
Mhm.
data requires when Greenheck tests these and creates these fan curves, they're using 3 duct diameters in and 3 duct diameters out. I do think we're going to get this later in the presentation, but these all represent ideal inlet and outlet conditions, and a lot of the times in your field you're not going to end up with that necessarily. I've seen a lot of elbow work before that will actually affect where that operating point ends up. And I think even in a constant volume application, it's still good to look to see where you are in relation to the motor system limit, which is that green curve right there. So the fan, the way it is selected, would not be able to operate past 1530 FRPM the way that it's selected right now. You may need a larger motor to get beyond that. And if you're in some unideal circumstances with the system, um, you may need more operating, I guess, more fan speed in this case. So
Yeah, larger range. That's
right,
actually
and
an excellent point.
right, and then on top of that too, just staying away. You'd like to. You're in a good spot there. Somewhat, you might need more distance from the motor system limit, but staying away from that surge curve is always a good idea. But then you are playing with fan efficiency, which we'll get to in a little bit. And I have had a few questions, by the way, about how the system curve is defined. That system curve right there, the dotted line going up, the blue one, that's always defined by your static pressure calculation of the ductwork. And
Right.
when you're applying the fan laws, the only way to apply the fan laws properly is on that dotted line. Okay, so fan laws wouldn't necessarily um, the fan laws wouldn't necessarily work if you don't have that ductwork calculated correctly, right? So we're dealing with ideal conditions here.
Yep. You're right. All my data as a manufacturer is taken exactly the way I was told to do it. It's in a perfect laboratory environment. You get out into the field and you have the real world interact. This is kind of what we're building up to in this webinar is to be able to understand that. And also, like the fan laws or affinity laws that I brought up, you're right. They're only accurate along lines of constant system resistance. What this means is when you did your test adjust balance, right, and you ordered it for 2 inches like we did on the screen, but you actually measured 2.25 inches, right? You can use that point that you are operating at, knowing it's at 2.25 inches, and you can project, well, if I speed it up this much, what will my new RPM be? You can project that, but only as long as you have not changed your system, right? I didn't change dampers. I didn't cut a hole in the side or have new outlets or add an elbow. I didn't change the system. So as long as the system is as you measured it in that tab, then you can project what'll happen in the future with changes in RPM. Absolutely.
Perfect. Thanks, Greg. Sorry to interrupt you there, but yeah, keep on
Not a
going. I'll
problem.
Yeah, and by the way, if you do have any questions, just type them into the question panel. We will have time to raise your hand at the end. So if you want to raise your hand and ask a question live, you can, but we'll save that for the 10 minutes at the end. All right, sorry, Greg. Sorry, Greg. Go ahead.
Not a problem. We're kind of moving right through these. So back to that min-max fan curve, whether it's a variable speed or a constant speed application, really, this is going to give me information about, is this a good fan selection? I mean, that's the answer we're all looking for today. How do I get a good fan selection? All right, let me point out last couple of things on this curve. The red line, that represents the RPM that my fan needed to move to interact at 2 inches and 1200 CFM. This green line, that is like the max as selected, right? So I'm telling you, this was ordered with a 1 horsepower motor, right? When I hit 1530 fan RPM, I will have consumed all of my 1 horsepower. That's my max fan speed. But notice there's a couple extra curves here. There's this bottom purple curve, which is a min, and a top purple curve, which is max fan curve as selected. All right, so minimum, that's kind of a gray area. That's us kind of giving you an idea. Okay, a typical turn down on most fans is going to be, say, down to 15 hertz or a 75% turn down. You know, this is just a rough idea of how far down you can go. But that top purple line, that is, through testing the fan characteristics or through the largest motor that can fit on this fan, this 2166 fan RPM, that's the fastest that fan can go, right? So this starts giving me a lot of really good information. I'm like, where am I selecting this fan compared to what can it possibly do? And right off the bat, I see here that, all right, I'm operating at 1448 fan RPM with the standard smallest motor that'll do this. I'm able to hit 1530, right? Some simple math. 1448 divided by 1530, 9.95. So I am selecting this fan knowingly at 95% of its capability. Okay, so is this a good fan selection, right? Is the ability to speed up 5% and speed down, 70%, turn down 70%. Is that what I want? Am I very confident in the design and installation of all the different parts that I'm going to be within that 5%? Some projects, you're going to say yes, right? Other projects, you're going to be like, I need more. I need more room to turn up, more room to overcome, you know, inefficiencies. All right. So in this scenario, I can look at this curve again and say, well, they show me my max construction limit. There must be motors I can upsize to that will give me access to that larger range. And that's exactly what we're doing here. If 1530 represented the 1 horsepower, maybe 1750 represents a 2 horsepower and 2166 represents a 3 horsepower motor. Right now, mind you, weight of the fan just went up with each decision. Cost of that fan went up with each of those decisions, right? A larger motor is going to cost more. But, what is the range that makes this a good selection for this engineer in this project? Also, one more thing about kind of good fan selection, you know, let's look at where that operating point is as compared to the do not operate zone, right? Am I in a good spot here? I am not right up against the do not operate zone, the surge line. Um, yeah, I'm actually pretty comfortable as we're operating right here.
Hey Greg, we got a question
Yeah.
come in. Is there a good rule of thumb for system static pressure? For instance, in order to account for unknown pressure drops in construction, would you want to add, say, 10% for static pressure when you're doing selection?
That is an awesome question, and I'll tell you right up front, I can't answer it. There is no good rule of thumb because every project, every one of your clients is their own beast, right? Um, there
Uh,
are a lot of times, firm rules that will give you guidance on recommendations there. You know, if your guidance is oversized, or over assumed by 10%, you know, um, just know that you may be in a larger motor than you would have been, but maybe that was the right choice. So that's kind of that's hard for from a person in my spot as a manufacturer. It's hard for me to give you too much clarity on that. But Matthew might, I mean, the mechanical reps that you guys have a relationship with, they
yeah.
may actually help.
So what I would say pretty much always have your operating power at least 10% below the motor nominal power. So if it's a 5 horsepower motor, I got to do quick math. Yeah, 4.5. So you would, let's say your motor horsepower is 5 horsepower. You wouldn't want your brake horsepower to be more than 4.5. That's typically what I see. I know that you could definitely make some sort of quick math equation to figure out what the um, static pressure percentage would be then. I can't do it on the top of my head, but it's close. Yeah, you could technically relate that to static pressure, but I do know 10% is pretty common when um, undershooting the size of the motor. So
One thing I can add to that is I can't, like I said, I can't give you too strict a guidance on that answer. But when I look at a good fan selection, kind of right what's on the screen here. I did that math, 1448 divided by 1530. If I'm doing a warehouse project, I got one section of ductwork that runs X number of feet. There is nothing to go around. I'm pretty rock solid on my math on the static pressure from that short run, right? So as an engineer, for me, I'm gonna play things a little tighter, right? I want the most cost-effective fan, with maybe a little less variability. Now, I start working in a hospital, or I'm working in a project with multiple inlets and curves, and we're spanning floors. There's room upon room for, inefficiencies to start sneaking in, extra elbows. Is 5% turn up a good idea there? Like for me, I start playing things a bit more conservative. And it's much easier for me, by the way, because I'm playing with your money, not mine, right? But I started playing more conservative. I like making selections where I'm at 80%, right? I have got a solid 20% to turn up, and usually about 60% to turn down. That's my conservative viewpoint from me as an engineer. So if you can take that guidance and maybe develop either what for your firm or for you, um, what is your comfort zone? And like I said, for me, my comfort zone depends on the project. All right, that was excellent. All right, just a couple. Oh, go ahead, Matthew.
oh no, so it sounds good. Yeah, that yeah, I would just say just make sure that your horsepower is lower than your yeah, what I said earlier. So go ahead, Greg, sorry.
Nope, that's awesome. And you're right. I mean, this on the screen that kind of plays into both what Matthew and I are saying, right? Here I've only got 5% to turn up. Is that, even within the horsepower recommendations by Matthew, if I just bump up to a horse and a half or a 2 horsepower motor, I added a little bit of cost, but I bumped up my range, so you can apply that across the board that way, right? I'm affecting my max RPM that is allowed. I do want to point out one more thing before I leave this slide. There are times where you're going to look at a min-max fan curve and you're going to notice that the green line and the purple max fan curve line overlap each other. They're the same curve, right? What's that telling me? Well, that's telling me A, there are no other motors available. This is the biggest motor. This is the max capability of this fan, right? So if you don't see that green line, just know that that is with your max fan curve. And in that scenario, is this a good fan selection? Back to that same question. You might want to look at bumping up your fan a size so that you have more room for different motor options. You might be operating in a healthier spot on the fan curve, right? Have more flexibility in what your turn up and turn down is, right? So I'm kind of maybe not telling you exactly how to do it, but I'm giving you the tools to make a good decision for yourself. All right, another one of those curves that help us make good decisions. Here's the static efficiency curve, right? You see that black dotted line. This is telling you where this fan's operation is most efficient, right? And okay, I'm going to go back on the screen. Right here is the peak of this curve. Oop. Um, boom. Right here is the peak of the curve. That is, if I was operating kind of in line with that, that would be the max operating this fan at its peak efficiency, right? And really what we're doing from here is if I kind of take the top end of that mountain and circle where it crosses our fan curve, if I select a fan operating inside of this range, I am operating that fan at a efficient point in its operation. Now, what happens if I am over down here? Oop, wrong button again. If I'm down here, right, can this fan move this air? Absolutely. It's right on the screen. The fan curve goes there, I can move it. Is that the most efficient fan to move that air? Well, not as much. When I'm operating in this efficient zone for this fan, I'm going to get quieter operation. I'm gonna make that dollar for electricity stretch farther, less wear and tear, right? If I'm operating outside in an inefficient place for this fan, louder, vibration will increase, right? Costs will go up for operation. And we can hit that even harder as we go through this and we start talking about like fan energy index, right? This is a great number to tell you where you're at on this fan curve. But this is another way of looking at efficiency. All right, I'm going to jump out of fan curves for a little bit here and kind of move forward. Um, let's look at fan impellers, right? There's different ways of moving air. First thing that is great news for everybody sitting here today. Everything I just taught you about fan curves doesn't change just because your impeller is different, right? That knowledge wasn't specific to a propeller or a backward inclined wheel, right? The how you read a fan curve and consume that data is the same. Now, where we're going to end up on the fan curve may be drastically different, but how you consume it is the same. There it is. All right, two of the most common uh, impeller types that we have in our industry of air movement, centrifugal wheels and axial propellers, right? And an axial prop, this is it's going to swing around, it's going to swat the air and move it forward. If you wanted to be really specific, creates a high and low pressure zone and air moves from high to low, and yeah, that sounds really cool, but it kind of swats it, moves it along. A centrifugal wheel, like this backward incline shown, this is going to draw air into the middle of the wheel and fling it out. It makes the air change 90 degrees in direction, right? And because of this, pushing air or, flipping it out, this is going to give these two technologies different areas where they're going to be peak efficiency, different areas where they're going to be desired, right? As you can, I mean, if you could think about a propeller, a propeller rule of thumb, um, my rule of thumb is, 1 inch of static pressure or less. Now, there are props out there. I know I make a few of them. that can handle 2.25 inches of static pressure. Yes, they are out there, but I'm just saying general rule of thumb. I stay under an inch. And the reason is as I'm pushing air, if I'm pushing air up against a concrete wall, right, that air is going to swing back and flip around the blade, right? Axial propellers are awesome at moving a ton of air, but against re, uh, less system resistance, right? It's too easy for the air to go backwards. Now, a centrifugal wheel, that is going to allow me to change air 90 degrees. So as I'm pushing air out, it's hard for air to then find its way back through a 90, right? So I have more capability of overcoming your resistance with that technology if the static pressure is higher. But then I lose a little bit of the top end of my CFM that's capable. And this is why these are both common, depends on your application. Let's look at, well, I'm actually adding a third technology here, and that's a mixed flow wheel. But the top left graphic, that's a prop. Air moves straight through. These are inline fans. The middle is showing a backward incline. I'm bringing that air in. I'm flinging it out 90 degrees. It's hitting the casing or the fan, and then it's changing another 90 degrees, right? So I got air changing 90 degrees twice. That tells me two things. It's going to be much better at higher system resistance, and it's going to take a little more horsepower because it takes horsepower to change air's direction, right? The third one, which is a mixed flow wheel is kind of a hybrid between a prop and a wheel. You're getting the best of both worlds. And you can see here, graphically, the air is changing at 45 degrees. Takes less horsepower to change 45 than it does 90, right? So lower horsepower. It's going to do it smoother, which means it's going to be a little quieter as well. So mixed flow wheels are becoming more and more common in our industry, and for this reason, low sound, high efficiency, and has a really good static pressure capability. So if I was going to look at a curve here and say, all right, static centrifugal wheels really going to just rule the roost in that high pressure, lower CFM realm. Uh, the propellers, they're going to be that high flow, low static realm. That's where they're going to be best at. In a mixed flow is actually kind of everything through the middle, right? Now, any one of these fans could operate at other points. This just comes down to, is it an efficient point of operation for this technology? And if you were to ask me, and it's a common question I get, okay, I'm looking at this graphic on your screen. How do I know if I've got the right fan selected? You know, well, I'm glad you asked because our next topic is going to be about fan energy index, right? What is fan energy index? Well, quite simply, it's a look at fan energy consumption that is wired to air, right? I bring in this much power, I move out this much air. It represents everything through the middle. So this is going to look at a fan and say, okay, all my losses, the motor I'm using, the technology of the motor I'm using, the type of impeller, all of that's going to be added up, and I'm going to have a ratio to work with. And that ratio looks just like this. On the right-hand side, I show you that the fan energy index equals baseline electrical input power over actual electrical input power. All right. What this is telling me is that, you know, a lot of data was grabbed on how fans are selected and how much power they use, and we are able to come to, and I say we as in an industry and AMCA, we were able to come to a conclusion on like this is normal, the normal amount of power to be used for a fan at this operating point. And if I take that over what you just selected, actual, I can create a ratio. And the way I would read that ratio is this. It's a beautiful one number, a 1.0 is saying, you know what, you selected a pretty standard solid fan, right? It's a good selection. If your ratio is greater than one, you picked a great selection. It's a really good selection. You're operating the right fan in its most efficient place, in its efficient range, right? And if you have a number below 1.0, we're just telling you the opposite. This is not a good fan selection, right? This fan that you chose might be able to move the air, but it's going to cost you, you know, it's going to be a less efficient fan at that operating point. So our graphic on the left here, I'm kind of showing you, okay, everything on this graph, whatever fan it is, I can move all these different airs, these different performance points. We got the gray area saying don't go in there. Perfect. We'll stay out of that. But then I've got, its efficient range, and then I've got, efficient, even more and more efficient range. And then I can get outside of that and say, you know what, this is a less efficient range. You can see where I'm in the FEI of like 0.9. So as a manufacturer provides this information to you, you can confirm, yes, I made a good selection on which fan it is, which size it is at this operating point. Now, I'm not saying you shouldn't look at the fan curve and make sure you're not in a bad place, or look at the min max curve and know where I'm at in my range of operation. Those are two variables that are important. This is just a third variable confirming that this is the right fan for you. All right, so we've been using as an example today a belt drive fan. Let's just look, the fan I used as an example, was it a good one? So under the green dotted line, everything under that curve, this fan can hit, awesome. Here in the dark green represents any point of operation for this fan where my fan energy index is 1 or greater. And glad to say, I guess I'm a pretty good engineer at this. I selected a fan at an operating point, 1200 at 2 inches, which was a 1.08 fan energy index, right? So I confirmed, I looked at the fan curve, it looked good. I had the right range for what I needed, and I'm operating at a good efficient point for that fan. And just kind of fill in here, FEI of 1.1 or 1.2, you can see the points of operation are just slightly different, but I'm in a solid selection right now. All right, that was a little bit of a precursor or an overview of fan energy index. I did not go super in depth with it, but luckily, Buckley has the online resources that they just mentioned at the beginning here. And I noticed that they have a, what is FEI webinar already recorded and there for your consumption. That's awesome. So highly recommend going back and checking that out. All right, I'm gonna jump back to fan curves. I just can't get enough of these, but I want to relate it to something that we even brought up in the beginning. How can I affect the fan curve? All right, so here we have our fan curve, 1200 at 2 inches, right? This is all that beautiful data that I collected as a manufacturer. And here's a picture of a fan being tested on a test chamber, right? An AMCA certified test chamber. And you can see I have air coming in one end, all smooth and perfect. I've got air leaving. I got fully developed flow, no elbows, no turning vanes, no dampers, none of that, right?
Hey,
Laboratory
Greg.
perfect condition.
Greg, I'm
Yeah,
so sorry to interrupt you. I'm going to interrupt you to go back for 1 second. We got a few questions that I would like to address really quick.
sure.
They're asking about FEI. So they're asking, is there a tool to check FEI on eCAPS? And first of all, yeah, FEI will be shown on eCAPS. And you might have mentioned this, but FEI will not matter for any fans below 1 horsepower.
I did
And
mention that.
okay, so that is important. So anything below 1 horsepower, FEI will not matter. You probably will be eventually constrained by like watts per CFM or something like that in the future on those, but at least in terms of FEI, it won't matter. Also, sorry, I don't know if you mentioned this or not, but right now in California, you actually cannot buy a fan with an FEI below 1.0. That's a California law, and as we all know in Massachusetts, we're not far behind them. So it will start to matter. I do have a question for you though, Greg. With the
Yeah.
FEI, with the FEI you showed on the fan curve, is Greenheck ever going to show those like clouds like that? on their caps fan curves?
I do not have a plan right now to represent FEI graphically,
Okay.
but that's not to say that it won't happen.
Okay. All right.
Right now, if you look in our eCAPS or CAPS programs, it prints on our submittals for 1 horsepower and greater applications. It's just given as a number.
Right. Can you go back one more slide too?
This
So yeah, so one of the questions was is the FEI. Yeah, the FEI cloud, the dotted lines you see right there, aside from the system resistance curve, obviously, that represents like almost like a topographical map of um the FEI available. So anything within that FEI 1.0 would be acceptable for now. And in the future, there's actually, and this is actually already happening in Rhode Island, we actually get incentives for better FEIs. So like if you get an FEI of like 1.4 on a fan, we can actually get your client will get an incentive, a kickback for having a more efficient fan. So a lot of this stuff will roll out. Greenheck is really ahead of it when it comes to this stuff, and that's why we're talking about it now. I do think this is going to be an important thing to schedule as we go. And good question, Ramy. What is the difference between FEI and FEG? I will tell you this: FEI is the efficiency grade of from the power line in to the air coming out. So FEG was kind of like an efficiency grade of the wheel and kind of how it operates, like kind of within the fan. But FEI is a more I guess a more strict, but really like a more whole, I
holistic
guess
view.
more whole, yeah,
Yeah,
more whole, right? Yes, more holistic view of the efficiency. So that's the inlet. Yeah, it's right there actually. Baseline electric input power versus the actual, um, wait, input power versus actual. Basically, it's from the line in to the air coming out. Essentially, it's the efficiency of
right.
the whole system, and it's actually dependent on the operating point, as you can see from this fan right, this fan curve right there.
Yep.
All right, so all that said, I guess I'm interested now. Actually, how does that has to tie into your system as well? Like the system effect could play with that a little bit if you think about it, but
Absolutely.
um,
You move around on where you're operating. If you have system effect, which we're moving into next, you can start pushing your point of operation into a less efficient or even a do not operate area real quick.
right. All right. That's all I have. There's a few other little ones that we'll probably address at the very end, but let's keep going. Great questions, by the way. I love seeing all these questions.
Awesome. All right.
So yeah, keep going. This next part that he's talking about is what I was talking at the beginning. System effect can have a huge impact on your curve, and more importantly, like when they're balancing it, we'll get a lot of questions like, "Oh, we're not getting, we're not your fan's wrong. It's not giving us the point we need." It's like, "Hey, let's back up. This is an AMCA rated fan. Like Greenheck is on top of it with this stuff. In fact, any AMCA rated fan, it's I would be really reluctant to question its performance capabilities. Usually, it's dependent on the actual setup, the ductwork itself. So
Yep. The
I would
installation.
always, yeah. So that this is really where that comes from.
All right. Well, if we look at it here, kind of back to where we were, this is as tested, right, in a laboratory condition. But this is my installation of this fan. All right, that does not look anything like what I tested. I have air coming in at an angle. I'm expanding or reducing. There was no way as a manufacturer I could represent what would happen to this fan's performance because of this specific installation, right? And if I were to project like what would happen to the fan curve on this installation, here I'm just going to give you a representation. That fan curve that I made as a manufacturer doesn't even exist, right? It's gone. The air's not moving in smoothly. It's not leaving smoothly. The fan curve, all that data I have, gone, right? So here I'm representing just, some really weird fan curve, what could be. And in the end, no matter what cool boogeyman name you give it, like system effect, you know, I need to move 1200 CFM. That need didn't change, right? So I'm gonna use those fan laws. I'm gonna speed up that fan and get back there, right? And you know what just happened? I sped that up. I am moving air much faster than I was originally designed to. My vibration went up, my noise went up, my horsepower to move that air went up, right? And I might even have to bump up the motor horsepower size in the fan to get into that range. Or, you know, in the worst case scenarios, I might have to actually pull that fan out and put a larger fan in yet that has a range to get there, right? So system effect, if I was going to define it, you know, it's when you change anything on the inlet or the outlet from how the manufacturer tested it, right? If you put a hard elbow at the inlet, you've created system effect. You've reduced that fan's capability to grab and move air efficiently, right? So I just wanted to represent that graphically on a fan curve since, well, we've been talking about fan curves and one more good site. All right. Let's kind of get in and you know we'll move away from fan curves. We'll walk over to making some selections here so you can see what I'm looking at, right? And I'm going to use two tools today. eCAPS is one of them. And that eCAPS tool, I mean, we're talking the 0 to 80% design phase. I love eCAPS. It is a great program. It's free to have an account. But to me, it's like a funnel, right? I start off with all the different fans out there that could do this, and I funnel down to the one or two that I want, right? The other half of this is our CAPS program, and this is that full boat program, and this is like an upside down funnel. I start with the one fan I decided I needed, and now I can pick all the accessories, the color, the disconnect, all that, fill in all that stuff to meet the needs of our clients, right? So the two programs work off the same database, kind of two different views. And eCAPS is short for engineering caps. So that's a great place to start. I am going to switch over to eCAPS Live, and I am sure
Um,
nothing can go
yeah,
wrong.
while you're doing that, Greg, couple things. We're getting a few questions now. Just kind of questioning what would happen if we do go into the surge curve. I know you mentioned it earlier, but I guess they're asking is it like the engine stalling or choking? What do you think?
Well, like most common hunting, stall, surge. Um, you know, surge. I mean, you can actually create a fan that will belch. It'll like build up pressure and then backflow. I mean, these things are what can happen in that area of operation, right? And that's why the manufacturer is saying just don't go in there. Um,
Yeah.
a lot of it has to do with the shape of the fan curve, and that shape of fan curve changes on if it's an axial versus a centrifugal, the size of the fan, the type of the fan, all those have effects on the shape of the fan curves.
And then kind of along those lines, Shane, I'm kind of answering your question a little bit here. Um, you know, I know that you just left that screen where you kind of estimated what the fan curve would look like when it's in
Mhm.
that when it has system resistance. It's important to understand that as a rep and at Greenheck cannot really model exactly what that fan curve would look like in the system resistant or sorry, in the with the system effect applied. And Greg was kind of just showing like a representation of what it could look like. It's kind of important to know that we cannot really give you an exact representation of what it would like look like. But that said, um, I mean, usually the best fix for a system effect issue is to fix the system. If you can make it any sort of fix to the elbows or some sort of upsizing of the ductwork, I know it's a huge pain, but it could be less expensive than replacing the fan, especially it'd be more efficient to do that as well. But any anything else to add to that, Greg?
Well, you know, and a lot of times, I mean, here's reality. when it comes to getting the right amount of air movement and a little bit of system effects in play, you know, if I had made a conservative or a really good selection up front, that fan might have the capability to push through it. I might have the room to turn up. Now that's minor system effect. You start going into major, well, we got bigger things to worry about. And the reality here is much of the time I fix what I can, and then try to speed up the fan for the rest, right? It's going to be a mix. If I'm 15% short on air and I can move the elbow at the inlet 3 feet away, and I've reduced the system effect drastically, so now I'm only 6% short on air. Well, now I'm in the range where I can turn that motor up a little bit, or I can turn that VFD up a little bit and get back to my desired goal point. So it would be perfect if we could always fix the system effect wholly and the fan performs per catalog. But the
Right.
reality is sometimes it's a mix.
Yeah. So, nice. All right. So we're gonna move on. I want to just emphasize really quick. He just mentioned this, and I'm gonna say the same thing. eCAPS is a great tool for engineers and contractors if you're interested to I guess in design build to do a 0 to 80% selection. So that's you're kind of trying to identify what product you need, and it'll do a really good job of funneling, like he said. And then caps, which is what the reps use, will really build out every little detail on that fan, every accessible possible, every coating, whatever it may be, is configurable within caps. But I want to also mention that that's give us a chance to help you out too with building your schedules. Reps, like me, like myself, or whoever you work with at Buckley, we can really help you work through all the details and stuff. And we can sometimes keep you out of trouble, but that's also what this whole webinar is about. We're trying to make sure that you have the tools necessary to do it right. And eCAPS is a great tool to do that. And I'll also mention that along the system effect lines, in eCAPS, there's actually a system effect builder that can actually it's still there, right?
Yep.
Okay, good.
I'll actually point it
Yeah,
out for you.
yeah. And we only have 30 minutes left, so I'll shut up now. But this is a great tool. But just keep in mind that you can always reach out to us to help out with your schedules as well. So go
And
ahead.
Matthew really, he brought up a great point that I can't emphasize enough. Your relationship with your mechanical reps is gold. This is, a group of people that have nothing but your best interest at heart, and they will lovingly come back to you and say, "Okay, I see what you selected here. Here are concerns." This is experience, and dedication to their craft that you have access to. That's pretty awesome. So. All right, I'll move on. I am in eCAPS. Right now, I am logged in as Greg. That's me. You can do everything I'm doing right now logged in as a guest. Okay. But what I want to do is make 3 simple selections and just let you see my brain as I go through those selections. Right. So here I am. I'm going to pick a fan. I want a downblast fan. Right. So I click on fans, and now I'm gonna go, okay, roof exhaust. This is this down blast. She's beautiful. That's the one I want. So I'm gonna click on roof exhaust. Now it's eCAPS is looking at all roof exhaust fans. So this is good. Back to, am I making a good selection, right? This is not just giving me down blast. This is giving me everything that's on a roof, right? So here I'm gonna look at 2500 CFM, and we're going to be fighting a 1/4 inch of static pressure. And we're in Wisconsin today, or at least I am. So 1198 feet, right? Now, I do apologize. This is live, so it's calculating through, and hopefully this goes quickly and smoothly. As I scroll down here, you'll notice I can like further restrict and define the fan that it's going to offer me below. I can even go in and say, I need to meet high wind, or I have a damper that's, I want you to account for the loss or the increase in static pressure, because I'm buying the damper, sold right with the fan. So you can go and further define this, but here's all the selections. eCAPS came back with 149 fans that are rooftop exhaust fans that move 2,500 at a quarter inch, right? So, right off the bat, ranking. When we rank things, and this is, you consume as you need. My ranking is developed off an algorithm of cost, um, cost to operate, and efficiency and sound, right? I'm using those and saying, okay, if I wanted to put something in front of you that was a good mix of all these, here's how I would do it. Um, but you can go through this entire 149 fan list and get just the right one you're looking for. A couple of things about this that you should know. Number one, let's say efficiency is an important thing for me, right? Here's FEI. I can click right here and it'll organize the fans by the highest to lowest fan energy index. If FEI was one of my criteria, I was trying to really hit. And I can do the same thing here. Maybe sound is really important. Maybe budget. Maybe budget's the most important on this project, right? So you can actually reorganize all this data by these points. Now, for me, I know I need a down blast fan, so I'm going to say, G fan um, to start, right? All right, so now it's only showing me G fans. And what I'm going to do, I got a G200 that's very green. Um, Really good FEI, awesome. By the way, when it comes to fan energy index, if you're ever trying to get a fan into a higher FEI number, there's two common methods. Number one, pick a more efficient technology, whether that be a mixed flow wheel or a EC motor. The more efficient motors. The motor's a big consumer of power in a fan. More efficient, bigger range. The other method is to upsize your fan, right? I can go from one size fan, go up one or two sizes, and I'm operating a large fan, moving slower, less noise, much more efficient. And you can see this here. I mean, my top two selections are both excellent fans. This one's smaller, has a great FEI, but it's lower than the bigger one. That just makes perfect sense then. All right. Now, one thing I want to kind of key in here, I put G in because I wanted to only see G fans. G represents the Greenheck direct drive version of a down blast, right? GB would be my belt drive version. In this scenario, I want efficiency. I don't want maintenance. If you were to ask me in our industry, we are definitely moving to direct drive fans on a whole. I mean, especially the big three, what I consider the big three. And that's simply this, like health, government, and education, right? I see very often that they are pushing hard to direct drive fans. No one's got a larger maintenance department than they had 5 or 10 years ago, right? We're all doing more with less. This is the world we live in. Belt drive fans, I have to maintain them. I have to tension the belts, replace belts. I got to grease bearings. Um, so if I can get that in a direct drive fan where I don't have to put that effort in to maintain the investment I made, awesome. Now, I will say this right off the bat. Belt drives will never go away. Belt drive fans have their niches where they are the right selection. Like if I have a high temp airstream, yeah, motors hate heat. Get the motor out of the airstream. Belt drive is perfect for that. If I'm at high horsepower, right? There are reasons out there that belt drive will never go away, but to put numbers behind it, 10 years ago, 80% of my fans sold in power roof ventilators was belt drive. Today, because EC motors are available, VFDs are available, 65 to 70% of my sales now are direct drive. I mean, so the entire industry in the last 10 years has completely flipped. All right, get off that and kind of move forward. I'm going to select this fan right here. When I select that, page pops open right off the bat. Really good stuff. I have got my fan curve right here. Let me see, I can't make that a little bit better to see. All right, I got my fan curve. I'm not at a bad place, a little less efficient maybe. Up here would be better, but not bad. I'm not right on the system resistance line. I can click here and view the min max version. This is a very green fan. It has an EC motor. So here I can see I'm operating at 970. I've got a good amount of distance between my max condition, right? So pretty good, solid selection. Um, we can even go into customize. And this is a great example of, like, hey, I could go up to a 2 horsepower here, right? Um, I didn't tell it anything different here. So I'm going to put in my tag here, EF-1. I upsize the motor to 2 horse. If we go back to my fan curve, something to notice here. eCAPS is not dynamic. It didn't change this line. Caps, the full boat 100%, that is dynamic. So if you change it to a 2 horse, it'll actually change your fan curves and represent that new max condition. So just kind of want to point that out. Really good information, height, weight, etc. Down here, oh, thing of beauty. You need 2D, 3D, Revit content. We're talking BIM. Um, this is an LOD or level of design 200 or 300, depending on which one you want to download. You have access to these. It's great. And we can print the cut sheet if needed. We're just going to do a quick add to schedule and close. And I'm going to go back here and we're going to make another selection. All right, let's make another selection. Let's do a blower, right? So a blower is a fan. By the way, Matthew had brought up earlier the system effects simulator. That is on our toolbox just to the right hand side. All right, blowers. Here, pick a blower. And I'm going to pick a blower at, say, 80 to 50 at 2 1/8 inch. Static pressure, still in Wisconsin. That'll go through and make that. I definitely recommend everybody come in and play here. You know, give a call to Matthew and his entire group and ask questions. If there's any, I'm kind of moving through this quickly. So if you want more information about this, please feel free to definitely contact them.
I'll take this time to ask a couple questions really quick if you don't mind.
Yeah, absolutely.
So one of my clients actually just asked, why did some of the fans not have FEI listed? It's
Good question.
I'm going to say it's probably because they were less than 1 horsepower, right?
Absolutely. And right now, there is no requirement for a fan energy index on anything less than 1 horsepower, nor
Okay.
is there really a test method to represent that. So this is why
Oh,
whenever you're looking here, you're seeing a dash for FEI. That dash is literally just saying it's a fractional horsepower. It doesn't fall into that FEI program.
right. So one of the questions was, where can we learn these abbreviations? Example, G for blow down. It's kind of funny. Greg and I've been doing this so long that we just know, but uh, um, if you use caps, Greenheck caps, not eCaps, it actually you would select what style you want first, kind of like what he's talking about doing, kind of like an upside down funnel, where you kind of know what you want and then you select it. But given that we're doing the opposite of that, I think in this case we're using eCaps to kind of figure out what's fan you need for the project. What you could do is kind of click, or can you hover over the model name? I'm not sure if that works that way. I think you can click the model name, just the model name. See what? Oh,
Yep.
well,
That shows a
that does.
picture of it.
Unfortunately,
Um,
it fully selects it, but it would show the picture of it, which would kind of get you to where you need. Usually, I'll say this: usually, Greenheck fans have like there's usually so like an abbreviation, or
mhm.
what's there, an
Acronym.
acronym. It's an acronym for whatever type of fan it is. So in this case, USF is utility set fan. It's kind of funny that the G is the only one that isn't that way, because G stands for Greenheck, because it was Greenheck's like first fan. They
Original.
built it in
Yeah.
like what 1947 or
Seven.
something like that.
Yeah. It
Yeah.
was the OG.
Yeah, it's the OG. That's why it's G. So there you go. But yeah, honestly, it's one of those things that over time you kind of just figure it out. And then one more question was, what temperatures are you referring to when you say high temperature airstream?
Okay, that's
Um,
a good one.
go ahead.
So, go ahead.
I think it's usually most of the Greenheck fans will be good up to 140, and then I think anything over 250 Fahrenheit is what we consider high temp. I believe. Is that right, or is it less than that?
You know, like for it depends on the type of fan. Like I belong to power roof ventilators. That's that spun aluminum stuff. 180 degrees is my line, right? If I'm moving greater than 180 Fahrenheit, I have to start looking at different construction. A spun aluminum may not be the right one at that point, right? So if I'm moving air from the ambient air from a building, it's 70-degree air. All right, that's perfect. If I'm over the top of a restaurant exhaust hood system, that's typically in the 100s. Those spun aluminums work really well upblast for restaurant exhaust. If I'm sitting over the top of a solid fuel, 400 degrees for hours, then I'm starting to look at different technologies. I'm looking at moving the motor away from that airstream. I'm probably looking at like a blower type fan that can handle those higher extended temperatures.
Awesome. All right, I'll get you back to it. Sorry, that was a pretty big derailment on my part.
Oh, not a problem. All right, so I'm picking this blower. My criteria right now, I'm going to say right off the bat, okay, I want to pick an efficient fan. So, by the way, if you use efficiency to verify your fan selection is a good one, and I recommend that. I even more recommend that this ends up on the fan schedule. And even greater than that, I recommend that you hold this number. I'm not saying which manufacturer you should pick, which bid you should accept. I'm just saying that you put all this time and effort into making a really educated, wise decision. Let's make sure that all bidders are bidding the same type and meet your needs, right? And that FEI is one easy one to hold to say, okay, I am getting an efficient fan, you know, right here. So just a little off there. I in my selection here, I'm going to say direct only, right? And efficient, and okay, this USF 30 B6. By the way, you can do all kinds of cool stuff here. I am being very quick. I could select several of these fans and I could show compare, and it compares the fan curve, size, weight, cost, sound. So you can do, all these different tools to help you make a good decision, right? But what I am going to do is pick this fan right here. Yeah. I'm going to go in, customize, and call this EF2. Awesome. It's got a 10 horse. I can even define three-phase voltage arrangement on a blower fan, defining, I want an upblast or a top horizontal um, type discharge. Boy, talk about keeping system effect from happening by defining your discharge, right? All these little things can come in and help you out. All right, I'm going to hit add to schedule. For time's sake, I'm going to kind of pause here and say, okay, we picked a downblast fan, we picked a blower. I showed you how to use different criteria to help me do my picks. Of course, I'm going to look at those fan curves and use those rules that we just went through to kind of validate my selection. Um, but this, in the end, I can add these to the schedule and, um, let's see here is, well, other than they didn't actually add them to the schedule, but they would add here. I could add notes, create a schedule. Even cooler is if I'm logged in, I can send this file to Matthew. He can consume this file and then just build out that last 20%. What disconnect, what color, um, you want an aluminum rubbering on that. All those nth degree type things that the full boat caps provides you. You can actually just go from eCAPS to caps kind of a neat capability. But with that said, I'm going to jump over to CAPS. Here's our CAPS program. And there, I can select by model. I can go through these trees to get to them. And this might be where, to help you out a little bit, if you do use full-blown caps, you can go to, okay, applications, fans, clean air, or I can kind of have it lead me there. Um, I myself am going to go here and shortcut it for time's sake. I want a G fan. Um, there's my mark. My G fan was say 2500 at quarter inch. So this is what Matthew's seeing, folks. This is kind of, all right, do I need spark resistance, high wind, seismic? Do I need to meet an efficiency code like California Title 20? If you say yes to this, I won't even show you a fan with an FEI lower than 1. That's 1 horse and up. Drive type, VFDs, I can do a lot of things from here, but here's my software. We had selected a G160 Very Green, I believe. Yes, we did. So I'm just going to click on that. Now notice right over here, much like eCAPS, here's my FEI column. I can click FEI and it orders it by FEI. Or maybe I'm doing a theater today, right? Maybe I might want to look at inlet decibels, and I can organize this by decibels to say, am I in that sub 70 decibels that I need for this application? Why look at all the ones that are just too loud, too big, or whatever for your application? In here, again, there's my beautiful fan curves. I've got a min-max fan curve. You can see my construction limits at 1200. That's for the motor that was provided with it. In this scenario, I could actually jump up a horsepower size to 2 horse, and now it actually moves that to 1725. It shows me that expanded range that I've got access to because I bumped the horsepower up. And from here, the nth degree of, I want a NEMA 4X disconnect that is fused. I want, these really different, really cool, very green controls. This is the power I have. I mean, there are so many things that can customize a fan specifically for your applications. But in the end, I wanted to make sure I made a selection in both softwares to kind of see how one can relate to the other. And if you created this in eCAPS and sent it over, they're going to grab it and basically your rep's going to have this far. This is as far as you got. They get to go through and fill in the rest of the pieces and parts for that. All right. I am going to bounce back to our presentation. Quick recap. I want to open the floor for a couple more questions here. Selection, good selection, good install means, well, success. Might have something a little bit more successful than what I'm showing on the screen, right? All right, folks.
I know
Kind
I know everybody's laughing at that.
of that is one of my favorite pictures, and that wasn't even a setup. That was real.
Wow. Is we got a pretty good Hall of Shame at Buckley. We keep that internal, but so I'm sorry. Were you closing out right now and opening for questions?
Yes, please.
Okay, so we've had a lot of great questions throughout. I'm gonna address a couple of these first before we kind of let people raise their hand. And if you have any questions along the way, please send them in and I'll address them that way. So, um, here's one. Clarifying a question on efficiency, we saw that up to there was okay. So when we were looking at static efficiency, we were seeing that it was only going up to about 60% efficiency on that selection, and she's asking, that seems slow, or sorry, that seems low, and therefore a poor fan selection if efficiency is a priority. Is that true, or is 60% static efficiency pretty normal?
So it all depends on the fan, right? The not just like manufacturer of the fan, the designs of the fan. Some fans, their static efficiency is a little higher. An inline fan will typically have a little higher static efficiency line or total efficiency line. I was showing you an upblast, so like 60% for that design is good. That's solid. That's normal. And I'm recommending that you operate within that top percentage of what is capable. You won't, the numbers are pretty tight. You're not going to find many fans out there that are, 98% efficient on moving air. So yeah, 60 would be normal for that type of construction across the industry.
Cool. Yeah, it really just depends on the fan. Um, and I, 60% efficiency sounds bad in like every other application, but when you're dealing with fans, it's not, you're not dealing with the same thing as like a indirect gas fired burner or something like that. It's totally different in terms of like
Different game.
energy usage. Yeah. So here's a question that I'd like to answer. Actually, one of the questions was: is eCAPS the recommended sizing for sizing slash selection tool for non-reps, or would it be worthwhile to utilize caps instead? So it's kind of funny, and I know Greg can add some information to this part, but eCAPS and caps has kind of been an interesting thing for me to navigate with a lot of all my clients are engineers. I like to kind of say, if you're not like dead set on a specific type of fan and you're kind of just like going into an application with an open mind about what you could do, use eCAPS, and then we can kind of work together on coming up with like more specifics on it. That said, if you're like, not to say that, if you've been in the industry for a while and you kind of know what you're looking for, I think caps is better personally. I use caps all the time. I mean, I only use caps. I hardly ever use ecaps. I will use ecaps every now and then if I'm like trying to like consider different options because it's more of a wider range of what it will show. But for the most part, I think caps is like, you kind of really know what you're getting from it. It's a little bit more in depth in terms of analyzing performance. Um, but there's really not really a wrong answer as long as you're not like trying to order it from eCaps because you can't do that. Um, so yeah, it really just depends. I would always recommend if you're kind of unsure to work with your rep, and we'll kind of help you get to where you need to be. But I think it really just depends on where you're at with it. Now, to that said, to make it even more confusing, and they haven't really announced it yet, they're actually coming out with a new version of caps as well. It's called TCAPS. Is that right?
Yes, and that's actually rolled out in August for some products. Just a
Okay.
different view on top of the program, but it's very helpful.
Okay, so I don't want to. Let's not focus on that too much. We'll probably send out a mailer about it at some point if it's as relevant. But I think it's almost like a combination of the two. I'm not really. I don't really. I really don't know anything about it. So, but I'd say if it's early design, use eCaps. If it's late design and you know what you're looking for, use caps.
I agree.
So early on, we had a hand raised, and you were in the middle of talking, so I didn't click on her. But it'd be great to have a live question if anybody wants to ask. It's your chance to talk in front of over 100 people. So go for it.
Millions of people.
Yeah, right. Not seeing it. Um, well, we're doing pretty well with time. We got 5 minutes left. Here's a question: how is FRPM calculated? Is it from the fan laws that you mentioned at the beginning?
So when I'm doing all that testing up front on a fan, I look at all those different points of operation and I understand what RPM I need to hit to have all those intersect, right? So I just know a final RPM. I know I need this fan at 1,000 RPM, and that's really what our selection software is doing. It's backward engineering what you're asking for. You're giving me the final output, and I'm calculating the input. So hey, you want this fan to move 1,200 at 2 inches? I look back at all those fans that can do that, and I say, okay, you wanted a down blast or an up blast, it's a CUE. What RPM do I need to run where I intersect 1200 RPM at 2 inches? So it's a combination of test data, fan laws help me get there, and then calculate or just come on, hey, this fan that you picked at this size, um, 1000 or 1400, whatever it was, that's the RPM I need to move your air against that resistance.
Cool. Well, that's the last question that has come in. I think we're gonna leave everything else to after this presentation. So I'd like to thank everybody for joining today. We really hope you found our webinar informative. If you'd like to learn more from Buckley, we have like 60 other webinars on our website, on our training portal that you saw during the presentation. And if you don't see something that you'd like to know about, please reach out to us, and we could either use it for an idea for a future webinar, or we could even do it project specific for your team. We love doing that stuff. And along those lines, anything project specific you have, please reach out to us. You can actually reach us if it's an engineering question at engineering@buckleyonline.com, or if it's project specific and you're already working with uh, if you're interested in working with Buckley, just reach out to your Buckley rep and they can help you out too.